This video is meant to help anybody who's struggling with the Lab 2 for Circuits 2. So I'm just going to demonstrate how I set up my circuit and how you should collect the experimental data. So here, let's start with Multisim. This is how I designed my circuit with these components, and these are measured values that I chose here. So here I have my Z1 load, or impedance rather, my Z2 impedance, and my Z load. And I have this running in interactive mode. Here I have 2 volts across my source and 1.2 volts across my load. So ultimately we're gonna reduce the circuit. We're gonna find the Thevenin and Thevenin so that we can remove this branch entirely and still have the same apparent voltage across this these 2 components here. So one thing to note is that when we use the function generator, we may not be able to use 1 volt peak to peak or 1 volt peak in order to get this apparent voltage. We actually may have to modify and use a different voltage in order to get the right amplitude. So here I have the physical circuit designed. I have these exact components placed, and when I go to measure the voltage, let's switch over here to the oscilloscope. What I'm going to do is I'm going to place my function generator, connect my function generator to my circuit. So positive side on the high end and negative here. So if you look at my circuit, I have my Z1 right here. It's a resistor and inductor. I have my capacitor value, and then I have my Z load here, this resistor and this capacitor. These are connected in parallel to this capacitor. So I'm going to go ahead and place the same way I want to determine my voltage across the entire circuit. I'm going to go ahead and place this oscilloscope probe across the entire circuit and connect a ground clip there to the leg, to this leg. A little tight, but it'll work. And then I'm going to place 1 probe across the load. So then we want to switch on our output. Let's take a look here at the oscilloscope. So I'm getting the exact same values as what I got in Multisim. I have 2 volts peak to peak across the entire circuit, and then 1.2 across the load. And this is the phase difference between voltage 2 and 1. And actually we can demonstrate that in Multisim as well. If I switch over here, stop the simulation, single frequency analysis. Make sure you do auto detect so it knows which voltage source you're using. You can have magnitude and phase for the number format you run. Okay, and here we're getting negative 46 degrees, which is exactly what we're getting off the oscilloscope. Okay, so the thing to remember here is that I am not using 2 volt peak to peak on the function generator. The function generator is not able to necessarily put out the exact voltage you need, so you will have to modify that amplitude in order to get the correct apparent voltage across the entire circuit. So I know that I need 2 volt peak to peak across these terminals here, and so I'm simply modifying my voltage output on the function generator in order to produce the right apparent voltage here, right? So this is something that we may have to do for the rest of the experiment. So when we want to determine the Thevenin and Thevenin, we need to take the impedance between these 2 terminals, A and B, which is where we're also going to have our Thevenin determination. So we can use the impedance meter that is provided in Multisim, and this provides, I already have my parameters in here, 1000 hertz frequency. It tells me my resistance and reactance. When I measured this on the LCR meter, I got a very similar value. It It was very close. It was almost exactly the same. So these are the values that I'm going to use in order to determine my Z Thevenin. If you look at your lab report, let's click this down. If you look at your lab report, you have Z Thevenin determination, which is made from your Z1, Z2 values. Now, I'm not going to go through these calculations. There's complex calculators online that you can use, and we've suggested using Hyperphysics, the AC Thevenin calculator, to do it for you, but it's fairly simple. So take your Z1 values, your Z2 values, and you should be able to calculate Z Thevenin. So when I did this, I ended up with exactly this value, right? So this is the resistance I'm going to use on my Z Thevenin load. And this provides me my reactance. In order to get the capacitance value, since this is negative, I need a capacitor, right? And then you use your reactance equation, the capacitive reactance equation, in order to determine the capacitor value that you need. When I take this value and I put it into my equation, I need this value for a capacitor. So again, I'm not going to review this. This is all stuff you guys should know, but I'm just kind of going through how to collect the data. So I have the resistance value, the capacitance value. This has provided my Z Thevenin, right? Now we need to make a determination about the voltage, the Thevenin voltage, and you also have that equation, right? This is the equation that you will use. Your Vs, make sure that if you're working peak to peak or peak, that you maintain that convention. So when I plugged in my values, right, 1 volt peak to peak or 2 volt peak to peak, and I have my Z2, Z1, Z plus Z2, I end up with 1.72 volt peak to peak and negative 32 degrees. The degrees is just the inverse tan of the reactance over the resistance. Actually, I can kind of show here the calculations. So when I plug in my values, right, I end up with 1.445 minus 0.927. So obviously you can convert this to polar form. You end up with a magnitude and an angle. So this tells us what we need to modify our function generator to. So if we look here, I've input these parameters. I've placed my Thevenin load here, and I have my Z load back in place. And yeah, when I run the simulation in interactive mode, I get an apparent voltage across the source of 1.72 volts, which is what I need, and 1.2 across the load. So we have the same exact voltage as what we started with in the first circuit, but now we're doing it for the V Thevenin and Z Thevenin. Okay, so when we go to our physical circuit, I've already placed those parameters that I needed into channel 2. Now notice that the amplitude does not match, but that's because I need to compensate a little bit, because the apparent voltage across the entire circuit is not what this is providing me. So I need to modify that a little bit in order to get the right apparent voltage. So I went from this circuit to this circuit here. I have my 73 ohm resistor. I have two capacitors in parallel that roughly equal 3.6 microfarad. I think this was 3.3 and then this was 0.4, so, other way around. And then I have my load, my original load, which is the 51 ohm resistor and a 1 microfarad capacitor. So let's go ahead and connect those. Let me quickly remove these connectors here. So we went from this original circuit. Let's disconnect all that. Okay. And we are now with our Thevenin equivalent circuit. I'm going to switch my micro grabber to the channel 2, where I already have my parameter selected. Okay, connect that. Okay, so channel 1 is going to be the measurement across the entire circuit. Right? And channel 2 will be the measurement across the load. So turn that on. Okay. So what do we get? We get the exact same results that we have in Multisim, right? I have 1.7 volts across the entire circuit. I have 1.2 across my load, so it's the equivalent voltage as what I started off with in my circuit, but it's my Thevenin equivalent. And I have a phase difference from the second to the first signal of negative 10 degrees. If I go to Multisim here, and I want to look at the phase difference between those two signals. Let me stop this simulation. Again, single frequency AC analysis, and negative 13 degrees, close enough. But that's the idea of how to collect the data. If you don't understand some of this material, the best thing you can do is make sure you just collect the data that lines up with Multisim or your theoretical calculations. When you get back to your home, then just work through it. Or feel free to ask the professor questions and understand what's going on. But the key thing to remember is that this function generator will not necessarily put out the right apparent voltage. You will sometimes have to modulate this in order to get the right voltage across the entire circuit. In this case, in the very first circuit, I went, rather than inputting 2 volt peak to peak, I have 1.7, right? When what I do there is that I make sure that when I connect the oscilloscope, right, in order to get to the right apparent voltage, all I have to do is look at what the oscilloscope has as the peak to peak function and line it up with what I need. I know that in the first circuit I needed 2 volts, so I changed my amplitude until it was 2 volts across the circuit. And in the second circuit I did the same thing. Rather than putting in 0.86 volts, I modulated that amplitude a little bit until I got 1.7 across the circuit. And then the Z load matches up. So the rest of the experiment works totally fine, but you have to assume that the function generator won't necessarily give you the right apparent voltage. And that's okay. As long as the rest of the experiment lines up, it's totally fine. So feel free to reach out to me or your professor if you have any questions, and we'll try to work through it.